Hi everyone, I'm Kathryn, a PhD student in the Chemlight Research Group at the University of Galway. Our research is mainly focused on using visible light to drive chemical reactions, and today I'm excited to share some insights into how we're enhancing the photoactivity and stability of ruthenium-polypyridyl complexes for the purpose of photocatalysis. So what is a photocatalyst? It is essentially a material that harnesses light energy to accelerate chemical reactions. The electromagnetic spectrum shown here on the slide encompasses all different energies and wavelengths of light. Since most sunlight falls within the visible range, our goal is to design materials that function effectively in this region. Ruthenium-polypyridyl complexes are popular as photocatalysts due to their well-known photophysical properties and long-lived excited states, which enable efficient charge separation to drive redox reactions. However, these complexes often form enantiomeric and diastereomeric mixtures, especially in ruthenium bipyridine due to its bidentate ligands. To address this, we synthesize ruthenium complexes with tridentate ligands to achieve a more linear structure, improving architectural control in supramolecular assemblies. The complexes used for this study were ruthenium terpyridine and ruthenium DQP. A major challenge with these complexes is their instability in solution, which requires anchoring them to stable supports to enhance their stability, recyclability, and overall photocatalytic performance. Various supports such as carbon-based materials, nanoparticles, polymers, and bio-nanomaterials have been explored in the literature. For our project, we chose graphene oxide, which is a graphene-based material with carbonyl hydroxyl functional groups. Here's a typical energy diagram for photocatalysis. When light is absorbed, electrons jump across the band gap from the valence band to the conduction band, creating electron-hole pairs for redox reactions. However, graphene oxide alone has a large band gap, making it less effective for photocatalysis. To overcome this, we pair it with photoactive materials, like ruthenium complexes, to narrow the band gap. In the case of water splitting, the conduction band must be more negative than the hydrogen ion reduction potential, and the valence band must be more positive than the oxidation potential of water. Shown here is the final structure of our material. The photoactive ruthenium complexes are modified to include carboxylic pending groups, and the graphene oxide is reduced to aminated graphene oxide, allowing us to anchor ruthenium species to the graphene oxide with an amide linkage. The Raman spectrum shows a clear red shift in the G band of about 15 nanometers, confirming the conversion of graphene oxide into aminated graphene oxide. SEM analysis reveals that both materials maintain a sheet-like morphology with little to no change compared to the unmodified graphene oxide. EDX elemental analysis confirmed the presence of ruthenium throughout both materials. Regarding photophysical properties, when anchored to graphene oxide, the materials exhibit shorter lifetimes compared to the free ruthenium complexes, indicating a quenching effect from the graphene oxide. This provides us with evidence of communication between the two components of the material. Both materials show bi-exponential decay, likely due to two different populations of the ruthenium complex that interact differently with the surface of the graphene oxide. Photostability tests show that ruthenium DQP, anchored to graphene oxide, maintains its emission intensity and excited state profile after 24 hours of irradiation, demonstrating good photostability. We tested photocatalytic performance using methylene blue dye degradation experiments with UV-vis spectroscopy to measure dye concentration before and after catalysis. Both ruthenium anchored materials showed promising photodegradation without catalyst leaching. Graphene oxide anchored to ruthenium terpyridine, however, demonstrated slightly less photodegradation power than the free complex in solution. More promisingly, ruthenium DQP anchored to graphene oxide achieved nearly 90% methylene blue photodegradation, a 10% improvement over the free complex. NMR experiments were conducted to analyze the photodegradation pattern of the methylene blue dye during catalysis. Upon light exposure, the aromatic proton signals showed deshielding and gradual broadening, consistent with literature reports of dye degradation via hydroxide radical formation. Finally, we subjected the materials to 3 photocatalytic cycles to assess their recyclability. The results were promising, with only a 2 to 3% drop in activity after run 3, proving these materials have good photostability over several cycles. From this work, you can see that we have effectively improved the photostability of ruthenium-polypyridyl complexes by combining them with graphene oxide supports, as well as their overall photocatalytic performance. Also, the recyclability of these materials should hopefully make them more applicable as photocatalysts in the future. Thank you all for your attention.